electrical systems, induction can occur between conductors carrying alternating current, or AC. When two conductors are placed near each other and carry current in opposite directions, they can create a magnetic field that induces an electromotive force, or EMF, in each other. This electromotive force can cause current to flow in the conductors, resulting in power loss and heat generation. However, the amount of heat generated by induction is proportional to the magnitude and frequency of the current, as well as the distance between the conductors. In the case of a large panel with high amperage conductors, the distance between the conductors is typically significant enough to minimize induction effect. The inspector's concern about induction problems is likely based on several factors. Firstly, the conductors are separated vertically, creating a longer path for the current to travel. Secondly, the conductors are in close proximity to each other, potentially increasing the magnetic field strength. Thirdly, the enclosure is old, which may not provide adequate protection against electromagnetic interference, or EMI. While it is true that induction can be reduced by keeping conductors together, practicality must also be considered. In this case, it may not be feasible to run the conductors close together due to space constraints or other factors. Additionally, the enclosure provides a degree of protection against electromagnetic interference, minimizing the risk of interference with sensitive electronic equipment. Measuring the amp draw of each circuit is not a reliable method for detecting induction problems. Induction is caused by the interaction between magnetic fields, which are not directly related to current draw. Based on the information provided, it seems unlikely that the separation of the conductors in the enclosure will create significant induction problems or heat generation. However, to address the inspector's concerns, the following steps could be considered. Firstly, provide additional documentation or evidence to support the claim that induction is not a problem. Secondly, install additional shielding or grounding measures to mitigate any potential electromagnetic interference issues. Thirdly, obtain a second opinion from a qualified electrical engineer or inspector. Induction is a phenomenon where a changing magnetic field produces an electric current in a nearby conductor. This effect is governed by Faraday's law of induction, which states that the induced electromotive force, or volts, in any closed circuit is equal to the negative of the time rate of change of the magnetic flux through the circuit. In simpler terms, when a conductor is exposed to a varying magnetic field, a voltage is induced in the conductor, causing current to flow. The strength of the induced current depends on several factors, including the strength of the magnetic field, the speed at which the magnetic field is changing, and the properties of the conductor itself. In electrical systems, induction can occur between conductors carrying alternating current. Because the current is constantly changing direction, it creates a fluctuating magnetic field around the conductor. If another conductor is placed nearby, this fluctuating magnetic field can induce a voltage and current in the second conductor. The amount of induction depends on the distance between the conductors, their orientation, and the frequency of the current. When conductors are close together and parallel to each other, the inductive effect is stronger. This is because the magnetic field lines from one conductor are more likely to intersect with the other conductor. Conversely, when conductors are far apart or at right angles to each other, the inductive effect is weaker. Induction can have both positive and negative effects in electrical systems. On the one hand, it can be used to transfer energy from one circuit to another, as in the case of transformers. On the other hand, it can cause unwanted noise and interference in circuits, particularly in sensitive electronic equipment. One of the primary concerns related to induction is heat generation. When current flows through a conductor, it generates heat due to the resistance of the conductor. This is known as joule heating or resistive heating. The amount of heat generated is proportional to the square of the current and the resistance of the conductor. In situations where induction causes additional current to flow in a conductor, it can lead to increased heat generation. This is especially true in high current applications, where even small increases in current can result in significant amounts of heat. Excessive heat can damage conductors and insulation, leading to equipment failure and potentially creating fire hazards. Another issue related to induction is electromagnetic interference. Electromagnetic interference refers to the disturbance caused by electromagnetic fields and the operation of electronic devices. Induction can cause conductors to radiate electromagnetic energy, which can interfere with nearby electronic equipment. This interference can manifest as noise, distortion, or even complete malfunction of the affected equipment. To minimize the negative effects of induction, various techniques are employed in electrical system design and installation. One common technique is to keep conductors carrying alternating current as close together as possible. This reduces the loop area between the conductors, which in turn reduces the amount of magnetic flux that can induce current in the loop. Another technique is to use twisted pair wiring, where two conductors are twisted around each other. This helps to cancel out the magnetic fields generated by each conductor, reducing induction. Shielding is another effective way to minimize electromagnetic interference. Shielding involves enclosing conductors or equipment in a conductive material, such as metal, which blocks electromagnetic fields. Grounding is also important for reducing induction and electromagnetic interference. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to minimize voltage fluctuations and reduce the potential for electromagnetic interference. In this specific scenario described, the inspector expressed concern about the separation of conductors in the electrical panel, suggesting that it could lead to induction problems and heat generation. The inspector's concern is based on the principle that separating conductors can increase the loop area and potentially increase the amount of induction. However, it is important to consider the specific context of the installation. Firstly, the conductors are enclosed within a metal enclosure, which provides a degree of shielding against electromagnetic interference. Secondly, the distance between the conductors is likely to be relatively small, which would limit the amount of induction. Thirdly, the current levels in the conductors may not be high enough to cause significant heat generation due to induction. In addition, practicality plays a role in the design and installation of electrical systems. It may not always be feasible to keep conductors perfectly close together due to space constraints or other factors. In such cases, it is important to weigh the potential benefits of minimizing induction against the practical considerations of the installation. Measuring the amp draw of each circuit, as suggested by the inspector, is not a reliable method for detecting induction problems. Induction is caused by the interaction between magnetic fields, which are not directly related to current draw. Instead, induction can be measured using specialized equipment, such as a spectrum analyzer or an oscilloscope. These instruments can detect and measure the electromagnetic fields generated by conductors, providing insights into the level of induction present in the system. To address the inspector's concerns, it may be helpful to provide additional documentation or evidence to support the claim that induction is not a significant problem in this particular installation. This could include calculations showing the expected levels of induction based on the conductor spacing and current levels, as well as measurements of electromagnetic fields using appropriate test equipment. It may also be helpful to consult with a qualified electrical engineer or inspector to obtain a second opinion on the matter. In conclusion, induction is a phenomenon that can occur in electrical systems due to the interaction between magnetic fields and conductors. While induction can have negative effects such as heat generation and electromagnetic interference, it can be minimized through careful design and installation practices. In this specific scenario described, the separation of conductors in the electrical panel may not necessarily lead to significant induction problems, especially considering the presence of a metal enclosure and the relatively small distance between the conductors. However, it is important to address the inspector's concerns by providing documentation, conducting measurements, and consulting with qualified professionals. In electrical engineering, understanding electromagnetic induction is crucial for designing and maintaining efficient and reliable electrical systems. Now let's delve into more detail regarding the scenario. The switchgear in question dates back to 1952. Older switchgear may not have the same level of shielding and grounding capabilities as modern equipment. This could potentially increase the susceptibility to electromagnetic interference. The fact that the grounded conductors and equipment grounds run up 5 feet and over 2 feet to be lugged in the neutral bar could create a significant loop area, increasing the potential for induction. The hot legs continue 2 feet on the bottom to be lugged to the bus bar. This configuration also contributes to the overall loop area. The inspector's concern about balancing issues is separate from the induction issue. Balancing refers to ensuring that the load is evenly distributed across the 3 phases of the electrical system. An unbalanced load can lead to excessive current flow in certain phases, which can cause overheating and equipment damage. To address the balancing issue, it is necessary to measure the current draw on each phase and compare them. If there is a significant imbalance, steps should be taken to redistribute the load to achieve better balance. Regarding the measurement of induction, an oscilloscope can be used to visualize the waveforms of the voltage and current in the conductors. However, it is not the primary instrument for measuring the magnitude of induction. A spectrum analyzer is more suitable for measuring the frequency and amplitude of electromagnetic signals, which can provide insights into the level of induction present in the system. Another instrument that can be used is a gas meter, which measures the strength of magnetic fields. By measuring the magnetic field around the conductors, it is possible to estimate the level of induction. In summary, the inspector's concerns about induction and balancing issues are both valid. While the separation of conductors may not necessarily lead to significant induction problems, it is important to consider the specific context of the installation, including the age of the switchgear, the configuration of the conductors, and the potential for electromagnetic interference. To address these concerns, it is recommended to provide documentation, conduct measurements, and consult with qualified professionals. Regarding the balancing issue, it is necessary to measure the current draw on each phase and take steps to redistribute the load if there is a significant imbalance. Let's consider the National Electrical Code, or NEC, guidelines related to conductor installation and grounding. While the NEC does not explicitly address the issue of conductor separation in the context of induction, it provides general guidelines for conductor installation and grounding that are relevant to this scenario. NEC Section 300.3 B requires that all conductors of the same circuit, including the neutral and equipment grounding conductor, must be installed together in the same raceway or cable. This requirement is intended to minimize the impedance of the circuit and reduce the potential for voltage drop and electromagnetic interference. NEC Section 250 provides requirements for grounding and bonding electrical systems. Proper grounding and bonding are essential for minimizing the risk of electric shock and reducing the potential for electromagnetic interference. In this scenario, it is important to ensure that the equipment grounding conductor is properly sized and connected to the grounding electrode system. The NEC also provides guidelines for the installation of conductors in enclosures. NEC Section 312 provides requirements for the installation of conductors in cabinets, cutout boxes, and meter socket enclosures. These requirements are intended to ensure that conductors are properly supported and protected from damage. In addition to the NEC, there may be local codes and regulations that apply to this installation. It is important to check with the local authorities to ensure that the installation complies with all applicable requirements. Considering the age of the switchgear, it may be prudent to have it inspected by a qualified electrician to identify any potential safety hazards. Older switchgear may have deteriorated insulation, loose connections, or other issues that could pose a risk of electric shock or fire. A thorough inspection can help to identify these issues and ensure that the switchgear is safe to operate. In conclusion, the inspector's concerns about induction and balancing issues are both valid and should be addressed. It is recommended to provide documentation, conduct measurements, consult with qualified professionals, and ensure that the installation complies with all applicable codes and regulations. Additionally, it may be prudent to have the switchgear inspected by a qualified electrician to identify any potential safety hazards. By taking these steps, it is possible to ensure that the electrical system is safe, reliable, and efficient. It's important to remember that the electrical system should be designed and installed by qualified professionals who have the knowledge and experience to ensure that they are safe and code compliant. Improperly installed electrical systems can pose a serious risk of electric shock, fire, and other hazards. In addition to the technical aspects of electrical system design and installation, it is also important to consider the human factors. Electrical systems should be designed to be user-friendly and easy to maintain. Clear and concise documentation should be provided to users and maintenance personnel. Warning labels should be placed on equipment to alert users to potential hazards. By considering both the technical and human factors, it is possible to create electrical systems that are safe, reliable, efficient, and user-friendly. Now, to further clarify some potential sticking points, let's discuss induction in more detail and touch on a few more points. Induction, at its core, is a phenomenon rooted in electromagnetism. Whenever you have a changing magnetic field, it creates an electric field, and vice versa. This relationship is described by Maxwell's equations, which are the foundation of classical electromagnetism. When alternating current flows through a conductor, it generates a magnetic field that is constantly changing in magnitude and direction. This changing magnetic field can induce a voltage in any nearby conductor. The induced voltage, in turn, can cause current to flow in the second conductor. The strength of the induced voltage depends on several factors, including the strength of the magnetic field, the distance between the conductors, the orientation of the conductors, and the frequency of the alternating current. The closer the conductors are to each other, the stronger the magnetic field they share and the greater the induced voltage. The parallel the conductors are to each other, the more effectively they interact magnetically and the greater the induced voltage. The higher the frequency of the alternating current, the faster the magnetic field changes and the greater the induced voltage. In the scenario under discussion, the inspector's concern is that the separated conductors will create a larger loop area, which will increase the amount of magnetic flux that can induce a voltage in the loop. This induced voltage can then cause current to flow in the conductors, leading to heat generation and electromagnetic interference. While it is true that separating conductors can increase the loop area, it is important to consider the other factors that influence induction. For example, the conductors are enclosed within a metal enclosure, which provides a degree of shielding against electromagnetic interference. The metal enclosure acts as a barrier to the magnetic field, reducing the amount of flux that can escape and induce a voltage in nearby conductors. The distance between the conductors is likely to be relatively small, which would limit the amount of induction. The closer the conductors are to each other, the stronger the magnetic field they share and the greater the induced voltage. However, as the distance between the conductors increases, the strength of the magnetic field decreases rapidly and the amount of induction decreases accordingly. The current levels in the conductors may not be high enough to cause significant heat generation due to induction. The amount of heat generated by induction is proportional to the square of the induced current. If the induced current is small, the amount of heat generated will also be small. It is also important to consider the frequency of the alternating current. The higher the frequency, the greater the induced voltage. However, in most power distribution systems, the frequency is relatively low, typically 60 Hz in the United States. At these frequencies, the effects of induction are generally not significant unless the current levels are very high or the conductors are very close together. In addition to the factors mentioned above, the impedance of the conductors also plays a role in determining the amount of induction. Impedance is a measure of the opposition to the flow of alternating current. It is composed of two components, resistance and reactance. Resistance is the opposition to the flow of current due to the material properties of the conductor. Reactance is the opposition to the flow of current due to the inductance and capacitance of the conductor. The higher the impedance of the conductors, the lower the amount of current that will flow due to induction. In conclusion, the amount of induction in an electrical system depends on a complex interplay of factors, including the distance between the conductors, the orientation of the conductors, the frequency of the alternating current, the current levels in the conductors, and the impedance of the conductors. While it is true that separating conductors can increase the loop area and potentially increase the amount of induction, it is important to consider all of these factors before concluding that induction is a significant problem. Addressing the inspector's concerns may involve providing additional documentation or evidence to support the claim that induction is not a problem in this particular installation. This could include calculations showing the expected levels of induction based on the conductor spacing and current levels, as well as measurements of electromagnetic fields using appropriate test equipment. It may also be helpful to consult with a qualified electrical engineer or inspector to obtain a second opinion on the matter.